and we start streaming. Okay, so last time I was like, oh, it's finally done, and then I realized my folly. It wasn't done. Grr. And now I know why. Okay. Wow, that was... I don't actually have enough info. I have to rerun it. Oh, that's so lame. Alright, well, whatever. I think I can just run this. Well, let's... Oh, fuck, no. Delete. Dude, it's like... Let's note. Hell yeah. Alright, we're doing it. We do be doing it, though. We do be doing it, though. Let's be real, though. We do be doing it. Hell yeah. Alright. Got myself some Chinese cartoons. Oh, this is so fun to watch. Just going up like that. Alright, so while that's going on, I'm going to get to reading my paper. Not my paper, but the paper that I was reading. I will continue reading it. I think this was the paper. No, okay. So the room, okay. Deep neural networks directly uniform with the image invading exponential generation problem. Among these methods, some approaches further use particular structural supervision to enhance the structure, completion, and final results, such as edge, image, and smooth image. Although these learning-based methods produce more realistic local details compared with early work, restoring reasonable image contents for more complex scenes is still hard, as shown in Figure 1. The main reason lies in that these methods fail to understand global context, but mainly focus on local texture consistency, which results in distorted global structure. Okay. Oh shit! I just realized that I want to stop this because I just remembered that I wanted to only select for things, yeah, I wanted to select for stuff that was of a particular kind. Yeah, specifically I just didn't want, I don't want anything that's like long panel page whatever thing, you know, like the manhwa stuff. Maybe in a different work. Unfortunately, it doesn't fit into my preconceptions. Original language. Yeah, original language. I guess I want this. I guess I want to set this. Um, I guess I'll do Japanese because I don't think that they're going to have any. At least if there is, it'll be an outlier, so I can just delete it. Whereas for Chinese and Korean, that's like the standard. So. Oh wait a second, it's probably gonna be JP and not Japanese. I think. Well, I'll find out if it gets angry. Yeah, okay. I think I can go ahead and get this now. Yeah, let's see. Okay. I think that should be good. Let's get back to this. So, local details compared with early work restoring reasonable image contents or more complex scenes is still hard to show in Figure 1. The main reason lies that these methods fail to understand the global context, mainly focus on local texture consistency. In contrast to the above literature, we suggest that the high-level semantics can be considered as common knowledge between specific pretext text and image in painting. The neural networks pre-learned for the pretext. That the high-level semantics can be considered as common knowledge between specific pretext tasks and image in painting, and that neural networks pre-learned for pretext tasks and provide strong global relational priors that can be used to infer low-level missing structures. Okay, so this is super interesting. I agree with this, right? I agree with this 100%. I don't think this applies to what I'm doing though, right? Because like in an artistic medium, and just any artistic medium, but specifically like drawn mediums, you're going to have objects which a machine probably will have never seen before, right? That like you can't even train them on. Like there's just an insane amount of categories for like objects, right? I think Resin only does like 1,000 different categories. And so yeah, I mean also Resin I'm pretty sure was not trained on like comic books and stuff, so I don't think that necessarily applies. But what you can do is find similarities, right? Like you should theoretically be able to like train a network to be like, are these two images the same? And so something I want to do is I might want to replace their ResNet thing with a network that's really good at determining like determining like object classes, right? And determining object classes, and then furthermore taking those object classes and it generates its own object classes for a given image. I think that could be interesting. Yeah, so to properly model global relations between missing contents and remainder, we take the high-level feature maps of a pre-trained multi-label classification model as the semantic supervisions. Various pretext tasks can be used to provide semantic supervisions. Notice we mainly use multi-label classification as typical pretext task without loss of generality. So yeah, I want to see how they use like how they use that on like an image with the things on it. What's the What's the dealio? These feature maps contain discriminative which can help these feature maps contain discriminative pre-learned semantic information of multiple objects which can help the global context understanding. Besides, as the pretext tasks mainly focus on abstraction of high-level features. Did this actually work? Oh, it did actually. Okay, cool. Someday. Who's speaking? I need to exit that. They improve, okay, as the pretest tests mainly focus on extraction of high-level features, they improve the robustness of our model to local textures and structural defects. The learned contextual features are referred to as semantic priors, and we visualize an example via the k-means algorithm. Yeah. Following this line, a novel context to our image in-painting model is proposed, which considers both local texture consistency and global semantic consistency. It considers both local texture consistency and global semantic consistency. Okay, interesting. The whole pipeline of our method can be summarized into two phases. In the first phase, we exploit two different encoders to separately extract the low-level image features and learn high-level semantic priors. Low-level image features and learn high-level semantic priors. By performing knowledge distillation on networks from pretext. Knowledge distillation on networks from pretext tasks. What is that? We do not train or fine-tune these models directly on the image imaging datasets, but only as existing models that were pre-trained on the Open Images dataset. Okay. We obtain the global context representations. In the second phase, the learned semantic priors are spatially injected into image features to help image completion. By learning and leveraging semantic priors, our approach, SPL, not only strengthens the local consistency of generated image, but also facilitates the structural inference of the missing contents from the remainder. Our contributions to image in-painting summary as follows. We show that distilling high-level knowledge from specific pretest tasks can benefit understanding global contextual relations, and is thus semantically meaningful to low-level image in-painting. There occurs no additional human annotations on the image in-painting datasets. Okay, we propose SPL, a new model for context-aware image in-painting, which adaptively incorporates the learned semantic priors and the local image features in a unified generative network. It is trained with a semantic prior learner in an end-to-end fashion. SPL chiefs. Okay, yeah, that's cool. Rule-based image in-painting. Okay. Alright, well, we'll see if it's any good. Alright, well, it's doing stuff. Good news. My mouse is jazzing out. Early work for image in-painting usually designs particular rules on low-level image features to establish the pixel-level mappings. More specifically, exemplar-based approaches exploit the patch or pixel similarities to directly copying textures and visible regions to missing regions. On the other hand, fusion-based methods try to smoothly propagate proper image contents into missing regions based on neighboring visible pixels. Although these methods produce vivid textures for simple background completion, they usually generate non-realistic images containing repetitive patterns due to the lack of high-level semantics. Learning-based image in-painting. Recent learning-based methods are mostly built upon generative adversarial networks and formulate the image inpainting problem as a conditional image generation. The work of context encoder first utilizes encoder-decoder architecture and proposes a channel-wise, fully connected layer to estimate the missing contents. Okay. Subsequently, the global and local discriminators are introduced by... Yeah, okay, I remember that one. To further enhance the constraints of local consistency. After that, a two-stage coarse-to-fine generation framework is proposed. Yep, I also remember that. With context attention module. To exclude the influence of invalid pixels during the feature extraction process. The gated convolution layer. And the region normalization block. So I think this is a different UNL than this UNL. So these two are the same, but this one is a different one. It's very, very confusing. Are proposed successively. Besides the attention mechanism, J et al. And multi-scale learning framework are also introduced. While these approaches use different network architectures learning image features, they usually fail to restore reasonable structures in complex scenes due to the unresolved context ambiguities. Yes. Right. That's where I think that there is room. I mean, I know there's room here. Structure enhanced image inpainting. To resolve the structural distortion of the missing contents, some two-stage models. First generated edges or smooth images and then use them to enhance the structural details. Other approaches also use edge-preserving images or semantic maps as extra supervisions and require dense human annotations on the image inpainting dataset. To resolve the structural distortion, some two-stage models first generate edges or smooth images and then use them to enhance the structural details. Okay, yeah. So yeah, this is really interesting because this is actually what the people who are doing the image fine-grained. I have no idea where it is now. Yeah. Manga, yes. Oh, okay, yeah. So that's actually what these people are doing, which is like fascinating. And like I legit think that there's like a lot of room for that. I think that definitely has its place. A very valid approach. I mean, it especially makes sense in this case, right? Because like that's literally what the images are composed of the vast majority of the time is you have edges, which are distinctly drawn in, and then generally speaking, they will shade it, you know? So, yeah, you have the inks, and then you have the actual coloring you're shading. Also reversing. Dense human annotations on the image inpainting dataset. In comparison, our model is trained on the image inpainting dataset in a fully unsupervised manner and only exploits pre-learned features from the pretext tasks, where data annotations are more accessible. Another difference is that in our model, the semantic priors are learned and spatially injected. Spatially injected. The semantic priors are learned and spatially injected into the image features in an end-to-end manner, which provides a more adaptive way for the restoration of the global and local structures. Yeah, okay. Approach. The overall architecture of the proposed approach is shown in Figure 2. We name it SPL. To highlight its ability to learn and leverage semantic priors, it contains three main components: an image encoder, a semantic priors learner, and an image decoder. In summary, the whole pipeline can be divided into two phases. In the encoding phase, we learn image features and semantic priors from the remainder of corrupted images. In the generation phase, the learned semantic priors are spatially incorporated into the image features to help raise relation the global and local structural contents. Okay, let's look at this. Overview of SPL. In the encoding phase, it learns image features FM and semantic priors SM from input via the image encoder EI, encoder image. It learns image features FM and semantic priors SM and the semantic learner. What does upsample mean? Semantic supervision, image decoder. In the generation phase, the semantic priors are spatially injected into image features via spatially adaptive normalization module. Aid. The semantic priors are spatially injected into the image features via spatially adaptive normalization module. What is that? That sounds very, very relevant. Whoa. Oh. There are three. Oh no, that's okay. It is two different U's, but it's yeah, okay. I was about to be like, what? Arc. Here we go. Image synthesis with spatial adaptive normalization. Image synthesis. See, that's kind of what I want to do, right? Like, I want to marry image inpainting with image synthesis. Because I personally think, oh, what? I actually want to do that. But just not right now. Because I do use archive a lot. So. Yeah, this seems extremely relevant to what I want to do. We have to wait. Yeah, let's finish reading. Let's just finish reading this, because otherwise I'm gonna go in the weeds. Context-aware image inpainting, we split the features of S of a multi-label classification model H. S of a multi multi-label classification model H as the supervisions for learning semantic priors whose parameters are pre-trained on the open image dataset and fixed during training. Models A through C are trained in an end-to-end manner. Image encoding. Yeah, okay. So image encoding. Given corrupted image IM and corresponding mask, locations for invalid pixels and zero gents. For those a valid pixel, we first utilize two different encoders, EI and EIO. No, I'm just EI and ES to learn image feature FM and semantic priors SM. These two features contain different information. We exploit different strategies to design architectures of these two encoders. They do not share any parameters. Image features and semantic priors. What is a semantic? Yeah, I guess that's what I don't know, is what is semantic prior and what is an image feature? We aim to extract rich, low-level features from visible contents to form the conditional input. These features play important roles in the vivid local textures. We exploit. Like, is this a common term? I'm just gonna look up semantic priors. Learn category level shape priors and object detection. Mean shape instead of weighted anchor points. Commonality of shapes. Similarity. We propose robust algorithms to match anchor points across instances that enable learning a mean shape as a category. Where? What is word? Ah, what? That's a bunch of BS. Well, okay, this is a term that people have used. I'm trying to figure out. Is a prior just like a previous, previously, or like an already known piece of information, and then it's a semantic prior, so it's like the. Yeah, it's just like the meaning of that object or whatever. Like it has an understanding of that category. Yeah, so I guess what I need is like some sort of machine, right? That is like these two things are part of the same category. Right? And like if you like no, then bad. Yeah, I'm thinking that this is an interesting topic. I want to continue. Extract rich low-level features from visible contents and form conditional input. From visible contents. So low-level features like, oh, this is a plane or something like that, right? Is that what I'm understanding? To perform the conditional input, these features play important roles in restoring vivid local textures. Therefore, we exploit two downsample layers to embed corrupted image into image feature. Details of Spade. Or what's my scraper doing? Okay, it's doing. It is doing, technically. Technically. Therefore, okay, so where I am is like that, and then M is an element of R FM something. H and W. What is H by W? Height by width? Probably. What the heck is C? The image features FM will be further fed to the generation phase to restore plausible visual details. To restore plausible visible details. I am a robot. I'm gonna be the first to die during the robot uprising. Semantic priors learning. For the semantic learner ES, shown in figure 2b, we aim to learn complete semantic priors for corrupted visual elements with supervisions from pre-trained deep neural networks. Complete semantic priors for corrupted visual elements with supervisions from pre-trained deep neural networks to understand the global context, which usually contains multiple different objects as shown in figure 2D. We exploit the multi-label classification model H retained on the open image dataset. The multi-label classification model H. Wait a second. So then H is something. Wait, is it? I'm dying. So here's a good question. What if you show two images to a neural network, right? And then you're like, okay, pick out the similarities. Well, an obvious way, or not an obvious way to do that, but one way to do that, right, is you get assign these a neural network, and then it assigns a particular encoding to each of those things. Diabetes. Is it wrong to say that? I don't know, dude. This is what people call it, okay? yeah. So then you take those encodings, right? But what if you want like fuzzy image boundaries, right? So what if you were to like highlight areas where they're like definitely in the same class? Oh man, that's so interesting. Oh man, okay. This has a lot of potential for sure. Also, I really hope that what I just heard was not like adrenochrome leaking out of my desk chair. It was like a liquid squish sound. So I really hope the yeah. I really hope the hydraulic fluid is in there is safe. Not, gonna be on my carpet. That would suck. Um, we aim to extract rich, low-level features from visible contents to form the conditional input. These features play important roles in restoring vivid local textures. Rich, low-level features. So again, what is W? Oh, it's M upside. Duh. Come on. This is the most obvious thing. What's wrong with me? I couldn't even figure that one out. Jeez. To understand the global context, which usually contains multiple different objects as shown in figure 2D, we exploit the multi-label classification model H, pre-trained in the open image. Yeah, okay. And we do not fine-tune this model on our image inpainting datasets. For this encoder, the texture details are less important, and the encoder needs to pay more attention to understand the global context in the remainder of the corrupted images. To this end, we make two modifications. First, as we aim to learn semantic information from higher layers of deep neural networks, we upsample the input images to preserve more local structures. Upsample them. Weird. We upsample the input images from local structures. More specifically, we upsample the full image. I is an element of 3. Oh, okay. This is height by width. I didn't. Okay. Yeah. Okay. So because that's one channel for red, green, and blue, and then the width and the height. Okay. So now I understand this better. So then M is, I don't know what the fuck M is, but the point is that C is a number of features or something, I don't know, some stupid like that. Anyway, I understand what these dimensions are now. Upsample the full image into a large one. I prime is an element of R, and the corrupted image and corresponding mask M are also upsampled in the same manner to form the input image. Why though? Like, hey, why do you need to upsample the image? I don't understand. It's not like upsample generates new information that you didn't know before. Unless you just wanted the thing to be more certain, or what? Like, I don't get it. Yeah, it seems like a pointless step. The corrupted image I am. I mean, unless you wanted to hallucinate information you didn't have before, then yeah, I don't know. It just seems strange to me. And the corrupted image and corresponding mask M are also upsampled in the same manner to form. for learning semantic priors. After that, we utilize I prime as the input to the pre-trained multi-label classification model H to extract feature maps. We utilize I prime, so I prime is the upsample image, as the input to pre-trained multi-label classification model H. Okay, so they upsample it to extract feature maps as the supervisions of the semantic priors. So, the goal is to... Wait, what? What is I hat? Wait, okay. I'm struggling here. So they're saying that this is the corrupted image. So, okay, so we're assuming that like it does have knowledge of what was here before. Right? It does have knowledge of what was there before. Right, but like, I'm so confused because, so like the previous inpainting methods were like, they're just like, oh, let's get rid of this person, right? Like you don't want to retain the semantic, you don't want to retain the knowledge that there's a person there. That's gonna like fuck up your results, right? I don't know, am I crazy? I guess I'll see where this is going, but it seems weird to me. It sounds really weird. I don't know, it feels like it's cheating. But I'll see. Yeah. After that, we utilize I as the input to the pre-trained multi-label classification model H to extract feature maps. Yeah, because it's like, if the thing is completely occluded, then what the hell? I guess maybe they completely get rid of that. They get rid of the semantic information that's occluded. Let's give me my guess. Like I don't know. I'll see where this is going, but like this seems a little bit. And the corrupted image I am. How many minutes? Oh, 42 minutes? Okay. Where's this at? Oh, what the hell? Oh my god. No. Literal for int with base 16 B. Well, wait, actually, that's a good question. Do I actually... So what all do I need to actually, like, download the thing? I need the chapter ID. So that gets me at the at-home server. But I need the hash as well. Fuck, and I don't record that. That means I have to run the whole thing over again just to find out if it worked. Well, what I can do is I can just be like, Yeah, no, I'm not collecting everything. I'm just trying out one. Yeah, it seems like it failed after that, so that ain't good, Chief. Oh no no, I already do that. Okay. Wait, so what was the issue? Yeah, I think I just need to make this handle exceptions. Alright, so I'm going to try reading the page. And if I can't read the page, then maybe I should discard the chapter itself. Yeah, I'm thinking that's probably for the best. If I can't read the page, then there's a really good chance that I'm missing like a really key piece of something. Okay. Yeah, so if that happens, then I'm just going to like ah. Do I make a directory at some point for this page? Ah, yeah, okay. So, if just downloaded equals 0, then I want to do chapter okay. I like that. Wait, how do I like force it to download? Or yeah. Oh yeah, yeah. I want an RM tree. I probably want shoe till, whatever the heck that is. SH util. That's probably what that means. Okay. Alright, hopefully that's enough error handling. You know, okay, I need to record more than just, because I need to record this as well. Yeah, okay. It does have the data. What is hash? Chapter attributes hash. Well, I assume that the hash... Yeah, I assume... Okay. Yeah, I think I need the ID and the hash. Right? Yeah, where is the chapters thing? Manga. Manga hash. Yeah, this is, I need everything. Okay, so I got the hash. Yeah, okay. I think hash is the only thing that I was missing before. But I get the page name from the... Oh. Oh. Okay. Record the manga. Page name. I don't have, yeah, I would need to perform a request of the page files, which I don't do. Also, I just realized I did not actually do the thing that I wanted to do, which is just funny. I mean, let's be real here. Okay, so we're getting the manga list. So get manga chapters. What does get manga chapters do? Yeah, the thing is, get manga chapters, like, it's a slow request. Just like, period. So, ideally, right, I would store the, yeah, because get manga chapters is where I get the page thing from. So I do these chapters, and then I do... So I really do need the pages. Oh no. I don't know. Maybe doing it as a CSV isn't the best idea then. Maybe I should do it as JSON. Yeah, it's probably a lot better. Yeah, okay. What does dump do? Oh, it's a file pointer. Okay. Okay, so I would just do JSON.dump. And I don't know, maybe like chapters or something. Oh, the object I need a file pointer. Chapter file. Okay. Let's try this. I would really like to somehow... Oh wait, I could probably just do that? No, it doesn't overwrite the file, which is what I would want. Like, I would want it to just continuously overwrite the thing. Which actually, now that I think about it, I totally could do that. There's like literally no reason that I can't. Yeah. Yeah, because it's like opening the file is legitimately going to take less time than like doing the than doing like the fetch request. So it's not going to affect anything. All right. I want to see what happens here. Oh shit. Okay, it's not getting anything. It's definitely because I chose original language. Okay, well, this should be my last thing tonight. Oh, you know what? I can look at example response. Free! What? So what is it? Maybe I just need to say Japanese? Well, okay, so that's an error. Why was it only... Why is this thing got 0? What? Well, this is lame. I know. How do I filter out? Oh, I don't know, dude. Well, you know what? I'll run it like this, and I'll just see what happens. I mean, what is the worst that could happen? That's a rhetorical question. My computer could literally explode. Which, that would definitely not be good. Ah. Yeah, okay. This works. Is it a little long? Sure. Okay, is this very long? Yes. Should I go for a different strategy? Probably, yeah. It's probably a good idea. Oh well. Alright then. I'm signing off for the night.